Hello! For today's mini lecture, I'm going to discuss a theorem from the end of our notes in lecture 27. That's going according to our total notes PDF on our website. So this is the last we'll see of continued fractions. The remainder of today's lecture I'll spend giving solutions to the last of the sample problems from the practice midterm, and I should have the actual midterm released about the same time that I'm uploading these lectures. So let's get started. The theorem that I'd like to talk about today is due to Dirichlet, who is interested in approximating real numbers by rational numbers. So the situation is we have some real number alpha. We want to approximate it by a fraction p over q, and we want this approximation to be close. Now, how do we measure that? Of course, with a large denominator, we can get better and better approximations, right? Think about just taking more and more decimal places if you are a fan of decimal notation. How can we weigh those different approximations against each other? Well, we can look at the denominator q, and we want the error in our approximation to be less than or equal to 1 divided by q squared. So here I do want p over q to be in lowest terms. And this is a question that is sort of tied up in the continued fraction stuff that we've been talking about a while now. Dirichlet's theorem gives us a new way to characterize irrational numbers. Right, so some real numbers are rational, they are equal to a fraction, and the vast majority of real numbers are irrational, they are not equal to any fraction at all. Dirichlet tells us that a real number alpha is irrational if and only if there exist infinitely many rational numbers p over q that satisfy this inequality that I've been talking about. So an irrational number alpha, say pi or the square root of 2 or e, pick whatever irrational number you want, there will be infinitely many approximations p over q that are within 1 on q squared of the number you are trying to approximate. The flip side of this is that rational numbers do not have infinitely many Dirichlet approximations, let's call them. So a rational number might have some approximations that satisfy this formula, but not infinitely many. It can only have finitely many solutions to this inequality. So how would you go about proving this? There's really two things you got to check. First off, let's think about what happens for an irrational number alpha, and the tools that I need to build up approximations I've already been talking about in my previous lectures. If alpha is an irrational number, then I know that alpha has an infinite continued fraction expansion, right? A0, A1, A2, and so on are all integers, and really this bracket notation is shorthand for the limit of the continued fraction A0 plus 1 over A1 plus 1 over A2, and so on. So with that idea, we can stop at k for whatever positive integer k is, and we'll get what I called a convergent. So this expression in the brackets will simplify down into a rational number. And you can check our previous lecture recordings to see that formula a bit more detail. And it was a property I showed that for any convergent pk on qk, the error between alpha and the convergent is going to be less than or equal to 1 over qk squared. This is actually a little bit weaker than the formula I showed last time. The upper bound is 1 over qk squared times ak plus 1. So you get an even better approximation if your next term in the expansion is a big integer. But that's all aside. We don't need that for the proof. The proof just says, can we find infinitely many rational numbers, p on q, that satisfy the equation? And sure, here they all are, right? For k equals 1, for k equals 2, for k equals 3, and so on. For any positive integer, I can come up with a corresponding convergent. Any one of them will satisfy Dirichlet's inequality. So that is our proof that irrational numbers have infinitely many approximations which are within 1 on q squared of your irrational number alpha. Hi, come here. So, what about rational numbers? What happens if we have a rational number alpha, and why can't I find infinitely many solutions to the inequality? So in the situation that alpha is rational, alpha has some expression as r divided by s. So let's just go ahead and say that r and s are in lowest terms. They're both integers. S is not 0. All the usual good fraction stuff we gotta worry about. What I want is some fraction p over q which is close to alpha. And I've just written it here as r over s. How close do I want it? It should be within 1 on q squared. On the flip side, I actually know how to subtract fractions, so I am going to raise the question, how close together could these fractions be? Or rather, what is a lower bound on this difference? So when I combine my denominators, my difference looks like r times q, take p times s, divide by sq. And I'm going to go ahead and say that this numerator is not 0, right? The only way I could get exactly 0 here is if both of these fractions were the same number, and that's too boring for approximation. So my numerator has to be at least 1, because my numerator has to be an integer, and I'm taking absolute values. Okay, so this difference, r on s, take p on q, has got to be greater than or equal to 1 divided by sq. So if this is my upper bound here, you can imagine the 1 on sq being my lower bound here. So if I put those together, this fraction has to be smaller than this fraction. That means that q squared has to be a smaller integer than s times q, or possibly equal to it, right? These are soft inequalities. Okay, well, both of these have a q in them. I can cancel that out. That means that q has to be less than or equal to s. Well, s is fixed, right? S comes from the denominator in the rational number I called alpha. So only finitely many choices of q are going to work for this inequality, right? Q could be 1, q could be 2, q could be 3, q could be as big as s, but no greater. That means that if I only have finitely many denominators I can work with, put them into this equation and get a good approximation, there's only going to be finitely many solutions, period. That's the reason why we cannot have infinitely many Dirichlet approximations to a rational number. That's the proof. I like to think about this a little bit informally to appease my intuition. So convergence are very special right? If I have some continued fraction expansion and I'm chopping it off short, I get a convergent, which is close to the value of the actual number I'm working with. And one of the things that makes convergence special is that they are the best approximation to alpha amongst all fractions whose denominator is q or less. So think about, I started off this series of lectures saying how 22 on 7 is an approximation of pi, and it's in fact a convergent to pi. So if you chop off the continued fraction expansion of pi in the right spot, you will get something that simplifies down to 22/7. That means that 22/7 is the best approximation to pi amongst any fraction whose denominator is 1 or 2 or 3 or 4 or 5 or 6 or 7. If you want a better approximation to pi than 22/7, your denominator needs to be greater than 7. And that is a property that all convergents have. If you want to have a better approximation than the convergent p over q, your denominator has to be greater than q. So if alpha is irrational, cool, that's great. But if alpha is a rational number, alpha itself has a numerator and a denominator. So when you get to the point that you're looking at denominators that are greater than the denominator of alpha, right? So here, if I'm thinking about a q, which is greater than s, as I called it in the last slide, then the best approximation to alpha is just going to be alpha. So at some point, there is no reason to try approximating your fraction by convergence anymore. You'll just get back to and say, well, the closest fraction to this number is itself. And then approximation is no longer an interesting question at that point. There's no reason to approximate, let's say, 230 on 17 with a denominator of 1,000, because you already know that you already have it completely defined when you're dividing by 17. There's no reason to approximate it any further. So this type of theory is really only an interesting question for irrational numbers, but as I was saying before, there are more of those than there are of rational numbers. So just sort of tying off our continued fractions section. There's much, much more further that a person could go with this, but we are only using them for approximating numbers in order to estimate numerators and denominators and attack RSA, so we are done with continued fractions at this point. Groovy.